Today, I'll be demonstrating the use of H2O in a predictive analytics use case. This use case is to predict the demand for Citi Bike bikes by station by day. If you're interested in replicating this demo yourself, you can download H2O from h2o.ai and go into our download page and downloading the appropriate version. And H2O is a complete open source product, so including the examples are available. So if you go out to the H2O GitHub, you'll find examples available, including this one, which is called the New York City Citi Bike demand with weather information. And you can click on that and get more information about the location of the data sets and the location of the script I'm getting ready to show you. I'll be demonstrating this primarily from R, but I'll also be showing you the H2O's flow user interface, which is a user interface that can be used to introspect your models or otherwise drive H2O. But primarily today we'll be using it from R. So let's get started. So the first thing to do to get H2O started is to actually just load an H2O library into your R environment. And then once you do that, you make a connection to your H2O server that is running. You can also use this command to launch H2O on your local machine if you want. First thing we need to do any predictive analytics is to load up some data. This data happens to be sitting in an S3 bucket, so we will load up the data. We're going to load up the big test data. We've got small test data, but we'll load up the big test data and make it available. So the first thing to do is to specify the location of your files that you want to load. So I've done that with one command. And now what I'm going to do is I'm going to import those files into H2O using the H2O import file command. We'll also time it so that you can see how long it takes to run this import and to parse this data. This data is being loaded up onto a server that's in Amazon Web Services. So H2O actually runs out of process from R, and what I'm doing is I'm making remote REST calls to the H2O server through the H2O library in R to command H2O's engine to load the data. While this is happening, the data is getting loaded and then it's getting compressed into memory. So you can see here it took just under a minute to load up about 10 million rows, and this is happening on one server in Amazon. We're going to do we're going to switch over to Flow, and we're going to take a look at some of the data that was just loaded from the H2O user interface. So H2O loads things into H2O frames. So we'll take a look at the frames that are available. The one I just loaded is called citibike.hex because I named it. We get information, summary statistics about all of these available in the Flow user interface. And also see that we're taking up 568 megabytes of memory to load this data. H2O does memory compression to make efficient use of memory. One of the interesting things is that summary information is also available here in R. So you can run many functions that are available in R on H2O frames and get back the same summary statistics. So the first thing we're going to do is we're going to do some light new feature creation or data munging. And what we're going to be creating is on that H2O frame is some information about which year the particular ride was taken, which month, which day of the week, Monday through Tuesday, or Monday through Sunday, for example, the age of the rider in years, and some other things like that. So we'll just highlight all those and run those directly in R. And while this is happening, what you're seeing is that code that looks much like our code works on your H2O frames too. So we're creating new columns on that H2O frame called data. For example, one called year to tell us which year the data actually ran on. We'll let that finish real quick. And then again, we'll take a look at those summary statistics on that data real quick inside of R. And so we can see, for example, these rides were fairly evenly distributed Monday through Wednesday with less riders on Saturday, for example. So that's available over here in your R summary statistics. And going back to the Flow user interface, now that I have that frame created, I can re-get the summary. And I can go down, for example, and look at that day of week column that was just created. And we can see now some graphical user interface of the days of the week. So most of the riders are middle of the week with less toward the ends and even lower toward the weekends, for example. We can also look at the ridership per month of the year. We can see that most ridings happened in the either the high tourist seasons or the warmer weather months of the year for this data that's been collected. So we'll go back to R. We'll do some more things inside of H2O. The first thing we're going to do is we're actually going to group this data by the day and by the station that's being run. So actually what we're getting is that we had data that's actually hourly. And so now what we're going to do is we're going to combine this using H2O's group by function, which is right here, to combine that. There's some data munging that has to happen when we do that combining. So for instance, trip duration, we're going to use the mean of the trip duration now as a new column. We're going to use the mean of the age. If you want information, all of this is in H2O's help, so you can see that how H2O group by works. So we'll go ahead and run all of this. We're also going to assign new column names. So what we're doing is we're creating a new data frame inside of H2O. In R, the handle we have for that is called BPD, and we're going to also assign that some appropriate column names. So we'll just run that real quick. So you can see it only took less than a second to group that down. Also, you can see as part of that grouping, we've taken those 10 million data points and now it's only 138,000 data points. Again, we can run summary statistics on the data frame we just created so that you can take a look and see kind of what's in there. So it tells you which day it was. This is the number of days after the epic, what the station was, which year, which month, which day of week, how many bikes were run inside of that hour, the mean age of the person, and then the mean trip duration. In H2O, we can also take a look at some other summary statistics. So for instance, we can take a look at the quantile information for the number of bikes per station per day. We can take a look at the mean age of the person that was checking those bikes out per station per day. And while we can also look at all this numerically, H2O has functions built in for some graphing of the histograms. So we can take a look at a histogram of the bike count per station per day. You see a typical sort of most stations had a very low number of usage with a few most stations and most days, with a few days and stations with a high number. We also take a look at the mean age and a histogram of that information by station by day. So the mean age was somewhere less than 40, most likely, but we can see that this is the distribution of the riders and their age. So with that, what we're going to do is we're going to define a very large function. I'm going to kind of walk through this function step by step. A function that will take this data that we now have by station by day and split it into a training, a test set, and then a final holdout validation set. we often run the models over and over again, so it's convenient to define a function so you can replicate them. And we'll show doing that here in a bit. So the first thing we're going to do is we're going to use H2O's random uniform to create a list of variables that are random uniform variables that allow us to make our train test holdout splits. We then go and split the data that's passed in into a holdout split that represents 60% of the data, a test set used for hyperparameter tuning that represents 30% of the data set, and then finally a test data set that for final scoring that holds out 10% of the data set. We'll print out summary data about how much has went into each one of those. We'll set the dependent column, which is what we're trying to predict on, which is the bike count. We'll set the input to be basically everything else that's in that, all the other columns that are available except for the bike count. And the first type of model we're going to run is a gradient boosting machine model. Gradient boosting machine model will be the first model we run. The next model will be a random forest model. And then the last model will be a generalized linear model. These are the typical hyperparameters that need to be set for GBM, which is the number of trees. The depth, which is the interaction depth, is set to 6, and the learning rate is set to 0.1. For random forest, we've set in some defaults of the number of trees and the maximum depth of the trees to be as shown here on the screen. And then finally for GLM, we're going to use an elastic net because the alpha parameter in H2O defaults to 0.5 with a small penalty parameter. If you're ever looking for more information on these, you can go to docs.h2o.ai, like I did here. You can select them. Select version 3, which is what we're using today. And then if you go to data science algorithms for H2O, you can find information about each one of these algorithms and then what each one of those parameters that I just showed you over in R. So we're going to start running each one of these. We're going to execute this, the rest of this, defining the rest of this method real quick. So just let me go through each one of those lines. And then at the end, what we're going to do is we're actually going to generate the R-squared scores for each one of these and then print them to the screen. And we're going to do it for the training test and holdout data sets so we can look at the performance. So now that we've defined that function, we'll start running these models real quick here. And then we'll take a look at what the results were, and then we'll go take a look at them in Flow. Okay, great. Our models have completed. Now we can look at the performance of each model on how well it fit the training, test, and holdout data sets. So we can see here that a GBM model that fit the residuals did a better job than the other two models, the random forest and GLM models, on really the final test set that matters, which is the holdout data set. It took about 3 3/4 minutes to run all 3 models and to produce those scores for them. We can get a lot more information available from those data sets if we want. One of the ways we can do is we can do it through R, but we can also go over and take a look at it in Flow. So I'm going to go over to my H2O instance. I'm going to ask Flow to show me all the models that have been built. And then I'm going to take a look at the GBM model that was built. So we can see here in the GBM model, we get information about the model parameters that were used, what the training frame was, the validation frame, how many trees, the maximum depth. We can see how the training and validation work went. One of the interesting things is that this model hasn't shown overfitting, which GBMs tend to do, so there's maybe even an opportunity to tune this model a little bit more. But it looks like it's largely converged, and maybe we're getting decreasing benefit for continuing to score in the model. We get information out like what variables were important in terms of bike demand. So from the data that we have available, We can see that which station was the #1 predictor of bike demand, followed by which month, and then finally days, which we will take a look. This is the number of days after the epic, so we can take a little bit of look at maybe some other models to try to understand that. We also get out various training metrics associated with this model. So we do get out the mean squared error, which is in this case on the training data was 130 bikes per day per station, and on the validation model 318. So while we have a high R squared, the mean squared error may be a bit high depending on what the demand looks like on a per day basis and what we're trying to get out of it. We can go up and look at, we're going to go pull out the GLM model and just take a quick look at it. So one, we can start and see more information about the model. Even though it wasn't the best predictive model, it does give us information about the data. So we can see that as years went on, basically we expect more riders per year. But that may be offset with the number of days after the epic. So there's maybe something going on in this data we'd want to spend a little bit more time on to try to understand what's exactly going on with it. GLM model wasn't great on this data, and we understand why, because, for instance, month was a positively correlated predictor, but we saw in the histogram that it had a bump in July and August. But again, we get all of kind of the training and validation metrics out, and those are all available. And we can see here that the mean squared error is really quite high for the GLM model. So one of the things we can think about is, can we improve this model? And one of the ways we came up with to improve this model was to actually include weather information into the model. So does weather affect people's adoption of Citi Bike? So we'll load up some weather data here. We have 2013 and 2014 weather data for the city of New York. To one station in the city of New York on an hourly basis. This data comes in. Some of the column names are kind of nasty. We'll take a look at those real quick just to see what they are right now. And so these are the column names. What we're going to do is we're going to just make these a little bit friendlier column names all the way around. And we're going to shorten up a couple of the column names to make it just to make them easier to operate and to demonstrate that you can do some of this in H2O. So like I said, we've renamed the columns, we've shortened some of the column names, and we'll just take a look at the top little bit of that data. So now that we've done that, what we want to do is that this is hourly weather data, but we're predicting by station by day. So what we're going to do is we're going to filter down and only use one of the 12 data points. So we're going to pick noon as the weather that's happening is noon as the weather for the day. That's just a choice we're making in this. You could make your own choices and play with this data and see if you get better information. One of the things we also notice in this data a lot, so we'll take a look at it real quick here, is that there's quite a few NAs on the rain data. So what we're going to do is we're going to assume that the NAs mean that it's zero rain. We're going to set that. And then we're going to rename a few columns. And the reason we're going to rename a few of these columns is that those are going to be the merge columns that we're going to use to merge that into the bike demand data. So I've renamed those columns to be year, month, day to match up with the bike demand. So now we'll just do a merge. And what H2O's merge function looks for is it looks for columns that match and then merges the data together. So it's a sort of lightweight join. At least one of the data sets needs to fit on one node, in this case the weather data. So we'll execute the H2O merge command. Just take a look at the top of the data, first few rows here. we can see that that data is available, and we can now see that we've got a few extra columns in here for prediction. So again, we will just simply run the predictions we ran before, except now with the data merged with the weather information. We'll take a look at the performance of the two together. Okay, now the model has completed. We can see we got a couple warning messages just to let us know. Those came out of the GLM model to let us know that there were a couple constant columns and they weren't included in the predictions. So we can also look at the performance of the models. Again, we see GBM kind of outperformed everything with an R squared of 0.96. We can also compare that to the previous model without the weather information, which was just up here. So we'll just quickly scroll up. And we can see that was about 0.962. So maybe weather didn't really improve the prediction of this model much. So that completes this demo of H2O for predicting bicycle demand around city bikes. Again, if you're interested, you can download H2O by going to our download page. And downloading the appropriate version. I've been demonstrating on this Shannon version today, but there's a new latest version that's available. And also all of these demos are available in our GitHub. And I encourage you to try out both the Citi Bike demo and the other demos that are available out here. So thank you for your time.